this video I'll be talking through the solutions to question 3 from the 2016 examination paper for numerical methods for partial differential equations. So here's question 3. The first question is all about using the method of undetermined coefficients to derive a finite difference approximation for this second order derivative. Okay, so undetermined coefficients, these are alpha 1, alpha 2 and alpha 3, and these are multiplied by the value of the function u to one step length h to the left of x, the function u evaluated at x, and the function u evaluated at one step length to the right of x. Okay, so the first question says write down first thing we need to do is write down the second order Taylor series expansions. Okay, so this is one step to the right of x, and you should be familiar with this. You're expected to be able to write down a Taylor series expansion. To write down the Taylor series expansion of x minus h, we simply replace h by minus h. So just remember that the minus h squared is of course plus h squared. Okay, the next thing we do is we substitute these expressions into the terms ux minus h and ux plus h to give you this expression. So the ones in the square brackets are the Taylor series. And next thing we do is we factorise out the u terms. So if we look at ux, that's multiplied by x, alpha 1, alpha 2 and alpha 3. So we have alpha 1 plus alpha 2 plus alpha 3. Do similar for the first derivative and the second. For example, the first derivative is minus h alpha 1 plus h alpha 3. And similar for the second order derivative. Okay, so to have an approximation, we want the left-hand side to be equal to the right-hand side here. So that means this term in brackets must be equal to 0. This term in brackets minus alpha 1 plus alpha 3 must also be equal to 0. And finally, this term in brackets plus a half alpha 1 plus a half alpha 3 multiplied by h squared must equal 1. Okay, so therefore that gives us the final expression. So this is a linear system. If we solve for alpha 1, alpha 2 and alpha 3, get these values here, and we just simply substitute them back in to this expression up here, and we have our second order symmetric difference. Okay, second part of the question, explain the term big O h squared and what it means as h tends to 0. Well, big O h squared are the truncation areas. So here we have big O h cubed. So this means all terms third order and above have been truncated from the Taylor series. Specifically for big O h squared, this means as h tends to 0, the error, which is this term, will tend to 0 at least as fast as h squared. And so therefore we say this is a second order accurate finite difference approximation up here. Okay, part B gives you Poisson's equation, which is a second derivative of the function u plus a second derivative of the function u with respect to x plus a second derivative with respect to y is equal to some function of x and y. Okay, in this case we have our function of x and y is simply x multiplied by y. We're given a rectangular domain. Okay, so x is between 0 and 4 and y is between 0 and 3. And x is discretized using 5 nodes and y is discretized using 4 nodes. So therefore the spatial length in the x direction is 1, because 4 divided by 5 minus 1 is 1, and same in the y direction. Okay, so the spatial length in the y direction is also 1, which is 3 divided by 4 minus 1, which is of course 1. Okay, so to derive the finite difference scheme, we replace the second derivatives here with our second order symmetric difference. Okay, here we've used subscript notation, so the I index refers to the x position, the j index refers to the y position. Okay, so we have that's our second order difference in the x direction and our second order difference in the y direction. F of x is x times y, so we have the ith coordinate of x multiplied by the jth coordinate of y. And what we now do is we'll want to rearrange to make u, ij the subject, so a bit of algebra, and we get down to this expression. And as I previously mentioned, delta y and delta x are 1, and this simplifies down to this. Okay, so essentially it's a quarter times the sum of the nodes to the north, south, east and west minus the x coordinate multiplied by coordinate. Okay, the second part of the question. Okay, so we're told that to reshape boundary conditions are applied at the boundaries. So that means all of these nodes here are constant and they have these values. These nodes in grey, these are the computational nodes which we're going to calculate. Okay, so we can apply this scheme here for each node. So I just take the first node as an example, U11. Okay, so it's a quarter multiplied by the node to the north, which is U12, multiplied by the node to the east, which is U21. Sorry, I'll say that again. It's a quarter multiplied by the node to the north, plus the node to the east, plus the node to the south, plus the node to the west. So it's U12 plus U21 plus 0 plus 1. And from that we subtract x times y. Now the x and y coordinate of this node are both 1, so that's going to be subtracting a 1, which gives us this term here. And if we do the same for the 5 other computational nodes, we get all of these values. Okay. Now we need to rearrange to make the unknowns, which is the u terms, all onto the left-hand side of the system. So that's what we've done here, simple rearrangement. And this can be written as this matrix equation. Part 3, briefly explain the difference between direct and indirect methods. Okay, quite simply, direct methods only require one application to compute a solution. So for example, Gaussian elimination or LU factorization. Indirect methods use an iterative scheme, so they keep improving on the solution until 2 successive solutions agree to a required accuracy. Now the reason why indirect methods are preferred is because this coefficient matrix can often be sparse, especially for a large number of computational values, and therefore the indirect methods are more efficient. Okay, and the final part of this question is edit a MATLAB program which will be given, which means we replace the question marks with appropriate commands to calculate a solution to this problem. Okay, so just going to scroll up just so we have the domain. Okay, and I'm going to bring in the Laplace. This is the Laplace.m program which will be given. Okay, so as you can see here, we've got some question marks we need changing. So nx is the number of nodes in the x direction. In our case, that was 5, and ny is 4. And the tolerance, which we've got to use according to the question, is 10 to the minus 6. Okay, so I'm just going to 10e minus 6 is 10 to the minus 6. Define x, y, u, and uk plus 1 arrays. So your x array will start at 0, dx is 1, and it ends at 4. And y starts at 0, dy was also 1, and that ends at 3. So just to show you where that comes from, it's the initial, here we are up here, where we define the domain. Okay, now we've got to define the initial value of u. So here are our initial values. Now I'm going to assume that the computational nodes have a starting value of 0, and we have these Dirichlet conditions. Now because with matrix indexing starts at the top left, and so this is the first row, this is the second row, I'm going to write down initially this matrix in MATLAB, but upside down. Okay, so the bottom row, I just bring that in, I've just forgotten, is 1, 0, 0, 0, 3. Okay, so that's the bottom row I put in first, and I also have 1, 0, 0, 3, and another row of 1, 0, 0, 3 again, and the top row is 2 with 2's in the middle, so I'm going to go 1, 2, 2, 2, 3. Okay, so I've defined that, and you'll notice that's upside down. There are other ways to do this if you prefer. Okay, if we scroll down to the next, here we are, the next set of question marks. So this is where I've got to input the Gauss-Seidel method for this Poisson's equation. So if you recall, this was 1/4 multiplied by the node to the north. Now notice what I'm doing here is I've got the j, the order of the index of ji. So j is a row number, I is a column number. So it's the other way around to how we normally write it in mathematics. So if I scroll to the scheme, as you can see here, we write uij, but when we do it in MATLAB, it's uji. Okay, so the node to the north is uj plus 1I, plus the node to the east, which is uji plus 1, plus the node to the south. Now the node to the south has already been calculated for the current iteration. So therefore, we could, with the Gauss-Seidel method, we use the k plus 1 value, and plus a node to the west, uk plus 1, j I minus 1. And from that, we have to subtract the x'th coordinate multiplied by the yjth coordinate. Okay, and if I look down, there's no further question mark. So this is just the lines code we were required to change. Okay, so I'm just going to run this program now, and I'm going to bring in the output, the command window. So here we have the command window, and you can see with the Gauss-Seidel method, have a look at the error. You can see the errors decrease over the iterations. Eventually they come to less than 10 to the minus 1. And this took 16 iterations for the Gauss-Seidel method to converge. And this last line here are the solutions correct using that tolerance. Okay, so then all we have to do is in our answer booklet is it said write down the solution correct to 4 decimal places. So that you can see I've written the solution correct to 4 decimal places down there. Okay. In the exam, you'd also be expected to save your program to the H drive.